Good day everyone, this is Klaus-Dieter. I am talking about mechanical behavior of materials. The course number is 315008 and we are writing the spring semester 2022. This lesson continues on dislocation theory. And today I like to investigate the analysis of stresses near the dislocation core. So we have introduced dislocation in the past. We have introduced screw dislocation, edge dislocations. We have introduced the characterization of dislocations and the Schmidt factor. And now I like to talk about the stresses. We know the dislocation puts some extra half plane into the crystal, and that exposes the crystal to internal stresses around this dislocation core. So, again, there are the two types. We have the edge dislocation and the screw dislocation. Which one you think is the easier analysis? This is a question to you. Do you have an idea? Put your hands up, please. I know it's difficult. The edge dislocation is maybe easier to imagine than the screw dislocation, because the edge dislocation just can be presented in 2 dimensions, the cross-section perpendicular to the dislocation line, while the screw dislocation has to be always shown in 3 dimensions. But actually it's easier to calculate the stresses near the screw dislocation rather than near the edge dislocations, as we will see here. At the edge dislocation, we have a displacement u equals a function u of x and y. So u is a vector of displacement which depends on x and which depends on y. So it depends on 2 coordinates. In the screw dislocation, if we write it down in polar coordinates, cylindrical coordinates, then we also have, or we only have a displacement uz, which depends on the angle theta only. So only depends on 1 coordinate. So how do we get these displacements around the screw dislocation? It is shown here. As we go around, once around the dislocation line, then we have a displacement by the Burgers vector b. And of course, this is the angle theta. So as we go theta equals 2 pi, then we have a displacement b. And this is what is shown here. Displacement b, Burgers vector, times the angle theta in radian going around. And of course, 1 turn is 2 pi in theta, so I have to divide it by 2 pi. That's the displacement of the screw dislocation. Easy. Shown here as well. So how do we get the displacement in the screw dislocation? We go once around here, the dislocation, and then we have a displacement of b and the Burgers vector b. So if we open the cylinder, we cut it and then open it, then the displacement as a function as a function of theta is b. Moreover, we can say the ux and the uy, they equal 0, and we only have the theta component. So we have no deformation in the x and the y system. As mentioned, uz equals b times theta over 2 pi, and now we can express theta by the x and y coordinates in Cartesian coordinate system, and then theta is tangent to the minus 1 y over x, and uz becomes a b over 2 pi tangents to the minus 1 y over x, arcus tangents y over x. Now we can take our formula for strains and stresses in polar coordinates. So we have the epsilon strain theta z component, which is shear strain, and that results, as we derived it earlier, 1/2 du theta over dz plus 1 over r du z over d theta. And that works out to be b over 4 pi r. The other components, they're 0. All the other strain components, so epsilon r is 0, epsilon theta theta is 0, epsilon zz is 0, epsilon r theta is 0, and rz is also 0. So very easy, we only have one component. We have the epsilon zeta z. So this is basically the shear strain along the z-axis in the polar coordinate system. And then we can put this epsilon zeta z into the constituting equations and get sigma, the stress now, the shear stress, sigma z, theta z equals 2 times the shear modulus, epsilon theta z, and this becomes g times b over 2 pi r. So we have the 2 here, which cancels one of the 2, factor 2 with the 4. So we have 1/2 times g, the shear modulus, and 1 over r dependence. All the other stresses also become 0. Resulting in, I put it here again, sigma theta z equals g times b over 2 pi r. And I put the r red because if we look as a function of r here, we see a singularity at r equals 0. So if r becomes 0, then we have a singularity. This stress would become infinity, and this is against physical understanding. So we don't have infinite stress, of course, when we go to 0. And this is where the model fails, because you remember these formulas here, they are for continuum mechanics. But if we go closer and closer and closer to the dislocation line in a solid, then we are not using a continuum anymore. We are using discrete locations of atoms with space in between. And that's where the model fails. So we can say around the dislocation, we have a dislocation core of where we don't have this linear elastic deformation. We have a different arrangement of atoms. They are arranged somehow, but not described by this very general formula. So here are a few numbers. Let's say we look to aluminium, iron, and silicon. We know aluminium is FCC, here it's written. Iron is BCC, and silicon is a diamond structure. It's a FCC structure, but it's of diamond lattice. It's not closed packed. This FCC here, typically we designate it for the closed packed face center cubic structure. Then we have the lattice parameters here, A. They're all cubic, yeah, so we only have A. And we have the Burgers vector, which I introduced earlier for the various systems. So in the FCC lattice is A12 so gliding of the Burgers vector along the phase diagonal. And in the BCC lattice, it's along the cube diagonal. While in silicon, we have also in the silicon lattice, diamond lattice, we have also the 110 component as a Burgers vector. These are now the magnitudes of the Burgers vectors. So 2 square root A12. This square root 3 is the cube diagonal. Half the cube diagonal, because we have the atom in the middle. and here also half the phase diagonal. Resulting in these numbers, if you put the A's into here, it's always important how you do it, because in the exams you maybe need to do these kind of things. You get the lengths of the Burgers vectors in nanometers, so 0.86, 286, 0.249, 0.384. We see the smallest is in iron, followed by aluminium, and well larger in silicon. Now we have the shear modulus in gigapascal here. We see they're increasingly from aluminium through iron to silicon. And we put that together, GB2 over 2 pi, and get those numbers. So aluminium, we get the smallest number, gigapascal nanometer. Iron, we get something around 2.1. And silicon, we get a very high level, 4.884. And also, we said there's the b over 4 pi we need as in our formula. So here, epsilon theta z equals b over 4 pi times 1 over r. So the b over 2 pi becomes 0.023, 0.020, close together, and a little larger, 50% larger, 0.031. So we put that together here on this logarithmic scale. The strain near this screw dislocation, which is given by this formula, epsilon theta z equals b over 4 pi times 1 over r. We have the 1 over r behavior, which is this slope. As we go to smaller r, we get higher stress, higher strains. And we see the two here, they're close together. You see the iron orange and the aluminium blue, they're almost superimposing, and silicon is half larger. But on this logarithmic scale, they are still relatively close together. Now putting the stresses, so you use this, GB over 2 pi, GB over 2 pi here, times 1 over r. You get those lines. So they're still distributed over half an order of magnitude, between 1 and 4, a little more than half an order of magnitude, but in the same order of magnitude. This is important. If we estimate orders of magnitude, we need to know the trend. So silicon is harder than aluminium and also has a larger lattice parameter, thus larger Burgers vectors. So the stresses, they also become larger. What we see here, it behaves very well at large, 10 to the 6, what is this, nanometers. So this is millimeter. But if you go 1 nanometer, we are here. And what happens if you go beyond that? If you go beyond that, then of course it saturates. Because as we know, we approach the atomic distance, we approach 1 Burgers vector, then the model is not valid anymore. So the stress field of a screw dislocation also can be written in Cartesian coordinates. We have done it in polar coordinates. So then we get, we have to put the sine function for the x and then the cosine for the y. And we get those formula, b over 4 pi times sine theta over r. And then we express r as well by x and y. So we get b times y over 4 pi x squared plus y squared. So the epsilon x z component depends mostly on y here, and it depends also on, of course, on x in the denominator. And the other way around, for epsilon yz, it's symmetric, you just swap x and y, so you got a b over 4 pi x over x squared plus y squared. And again, all the other components, they result in 0. So now xx, now yy, now zz components, and now xy shear component. Only in the z direction we have the shear component. Resulting into stresses, so we have shear stresses, tau xy, then you can work it out, a similar coordinate transformation. We get minus gb over 2 pi, and then the coordinate dependence is y over the radius squared. And for symmetric, for the xz, we get x over the radius squared. And all the other stress components result in 0. Easy. One interesting feature is, if we look here into the formula, we have the sigma, only a shear stress in sigma zz. That means as we go along the z-axis here, we go along the z-axis, then we get a shear. And that shear gives you a torque as you go along. And this torque can be seen by elastic relaxation, that around the dislocation core you get this screw torsion of the crystal lattice. And that has been observed by this interesting crystal feature here. So you see, here's a sketch. So we have here the single crystal whisker with one dislocation, one screw dislocation in the center. And there are arms of twins grown regularly, more or less regularly, along the distance here. And you see that the orientation rotates of these twins. They're always in the same crystallographic orientation of the whisker, but it rotates as you go along the z direction. And this is because of the torque of that dislocation line, the torque of the screw dislocation. So a very nice demonstration which you can look up in the book here about dislocations. Or there's a reference to literature as well. Nature Nanotechnology 2008. So look it up. Always good to see these original papers. Right. Now, I introduced the screw dislocation. Let's talk about the edge dislocation. As mentioned, the displacement is u equals u of ux and uy. Well, it's a function of x and y. And so it has two components. The third component, uz, is 0. That means perpendicular or along the dislocation line, perpendicular to that cut we show here. We don't have a dependence, only in the x and the y direction. And we insert a plane from the top here. So then we can write down the sigma xx becomes, we have this factor again, minus gb over 2 pi. We get a 1 minus nu and this coordinate dependence. I don't go through all the details, but this is the coordinate dependence which you finally get if you look it up, for example, in this book, Introduction to Dislocations. They have the mathematical derivation of those formula. Sigma yy we get a y times x squared minus y squared divided by the radius squared. So here we have a 3x squared plus y squared divided by the radius squared. And tau, the shear stress, is x times x squared minus y squared divided by x squared plus y squared. I don't derive this because the notes say it's very complicated and we don't learn much from the mathematics behind. It's really just the result which count. So people have solved that. You can look it up. There's a long mathematical derivative, pretty complicated. We don't do that here. But we need to understand what's happening here with these stresses, how they depend. We see already they depend somehow with 1 over r. So if we put it back into polar coordinates, we have a sigma r, and we see there's a sine theta over r. It's a 1 over r behavior. And here in the other direction we have a cosine theta 1 over r. So as we go around here with theta, yeah, this is theta. So basically, apart from the sine and the cosine, which makes sense because we have that edge, so if you go horizontal or vertical, it scales with the sine and the cosine. But basically, we have just this prefactor, and the prefactor, let's say the maximum amplitude of that, just differs from the screw dislocation by factor 1 over 1 minus nu. So basically screw and edge dislocation over the thumb, they just differ by a factor 1 minus nu, where nu is the Poisson's number. If we visualize these stress fields, so here we have these formulas to the left. If you visualize that qualitatively, then we get this behavior. We have, let's say here, sigma xx above the dislocation habit plane, which is shown here, this black line along x, the 0 of our coordinate system. Above we have compression, so it makes sense. We introduce here an extra lattice plane, so that compresses the surrounding lattice in this area. And the same here, it pulls at the bottom, it pulls the lattice further apart because we want to accommodate these extra atoms. So below this plane, we get tangential, we get expansion. So expansion is a positive stress, and the others compressive stress. So sorry, this is minus here. This is a minus, the green one. So this is in the x direction. We can imagine that. Also, in the y direction, we understand the same thing. If we get compression in the x direction, then we get some hydrostatic relaxation. We also get compression in the y direction. Yeah, it wants to push this plane out. So in the y direction we also get compression, or we also get expansion below the habit plane. Now let's look to the shear, so the sigma xy. Sigma xy, of course, if I introduce a plane here, and let's say I look to this location along this line here, then I have a shear stress. Here, these atoms, they get displaced to the right, and those atoms, they are closer to the left. So that gives me a shear, which is then positive in this direction. And of course, if I go to the left side, it's the other way around, yeah? So I get the shear like this on the left side, which we call negative. So the one we call positive and the other one we call negative. Some people ask me about the sign of the shears, and that has to do something with the handiness of the coordinate system. But it's symmetric. If you have it in one direction positive, then the other direction must be negative. Or if you have a mistake in the sign, then this would be negative and this would be positive. Depends on which direction you're looking at. Right. So the shear is a shear like this or a shear like that. The one is positive, the other is negative. And if I turn around, then it's just the left and right hand side is changed. Yeah. So if you get the coordinate system right-handed, then the positive is as shown here to the right and negative to the left. So we qualitatively understand these figures. Obviously, if I go somewhere here, in this point, there's no shear. Yeah, there's no shear. That's what this dumbbell means. So here we have a positive if we go along the x direction, but if I go along the y direction, the shear is 0. So the length of this, you can draw a length of vectors, of lines, to the borderline. And the length and the direction of this vector gives you the magnitude in this direction. So the length in the vertical direction is 0. Also here in that diagram we see these octants. We divide the circle, the area, into 8 parts. Yeah, we have here the part where we have a compressive stress, expansive, tensile stress, or also tensile displacement, tensile strain. No, it's compressive at the top. So compressive here, we said this is the negative, green, yeah, here is also green, yeah, and red is red, and green is green between the two figures. Sorry for that confusion. So here we have the compressive. We have compressive in this direction. We have compressive in this direction. We have compressive in the y direction as well. So these are the normal stresses, the green arrows in those two octants. But we see the shear changes. Here we have the shear component like that, and shear component like that. Of course, sigma xy equals sigma yx because of the symmetry of the tensor. And if we go to the left side here, then it just turns around. So that goes from the positive to the negative shear, but both normal stresses, they are compressive. Then in this quadrant, octant, we have a compressive stress in the x direction and a tensile stress in the y direction. And the same here, or opposite here at the bottom, in that octant, we get compressive vertical along y and tensile along x direction. And then symmetric, tensile here, tensile there, compressive and tensile there, tensile and compressive there. So let's remember these octants where we have the different situations according to normal stresses and shear stresses. That's an important diagram which visualizes, which gives you a map what is happening in which of those octants. Right, so these were now shear stresses and shear strains, or the strains and stresses, shear and longitudinal, around the two types of dislocations. Now I like to introduce the strain energy of the dislocations, again, first of the screw dislocation. So the dislocation is a line defect which increases the strain energy of the material. If we put a dislocation into the material, then we get the stresses as shown, and that increases the stress field, costs some energy. So let's look to the elastic energy, which is integration over the strain field times the stresses. So the stresses integrated over the strain field. And for linear elastic material, we get 1/2 sigma ij times epsilon ij. So it's a summation over all the components. And we can say for this linear material, the total energy is the core energy plus this elastic energy. So we say now, if we have the body here, we have the dislocation, and we say there's a little core in which our formula fails because it becomes too optimistic. So we say this is a core energy, and we only start this 1/r behavior outside the core, for which we calculate the elastic energy, EL. So we have sigma theta z equals 2b over 2 pi r, and we have the strains b over 4 pi r. We have had that before. And then get for the elastic energy this expression gb squared over 2 pi r to the square. Also, the work, if we look to the work, the total energy needed is the integration of the elastic energy times the volume. So we integrate over the volume. This is the total macroscopic work. And we can now express the volume by the area dA of the dislocation times the length of the dislocation. So we introduce the length of the dislocation R to get an energy per unit length of a dislocation. So W over L. L, we work for a unit length, L, or per length. So we normalize by the length and get then the work per length, which gives this expression. So integral from R0, this is the size of the core here, to the radius R. So the R we're looking at, infinity, maybe not. So this is where we don't feel the dislocation anymore, we will see. And that then becomes, with all this, GB squared over 2 pi, 2 pi r squared, 2 pi r dr. 2 pi r is the area, yeah, we have the dA here. And that becomes finally this formula. So we can integrate the 1 over r, giving a logarithmic function. So GB squared over 4 pi times r over r0. And we say this r0, if r is smaller than r0, so inside the core here of size r0, we have a nonlinear elastic zone where the solution, this 1 over r behavior, is not applicable. The atoms, they are arranged somehow in a convenient way, but how they are arranged, this is not the topic here. We know they may change, of course, they change crystallographic symmetry in there. Yeah, it's not a translation invariant lattice in there. So we get some other nonlinear behavior inside the dislocation core. So we just keep in mind there's a radius r0 and the work per length, so strain energy per length of the dislocation is for the typical R we put in here is a half spacing between dislocation. So if one dislocation here, how far the stress field goes? Well, if I have another dislocation here, then I say, okay, until half this area, I concentrate on this dislocation, and then it becomes smaller as I go to the second dislocation, and here that second dislocation becomes dominant. So I say that for the typical R, I put a half space between dislocations. And now I can look to numbers. I can say, okay, this half space, the R is cut off at 15 times R0, or 20 times, or 50, or 100, or 1,000, or 1 million times R0, just for these cases. And let's take the ln R over R0, which in the first case, ln of 15 is 2.7, of 20 becomes 3, 50, 3.9, 100. For 1 million, it becomes 13.8. So we see these numbers, they're not even varying by 1 order of magnitude. 1 order of magnitude would be 2.7 to 27. So they're varying somehow just half an order of magnitude, because it's a logarithmic behavior. And that number, which becomes an average number, really depending on your dislocation configuration, we put this into a factor alpha, leading now to the formula GB squared over 4 pi, which is repeated here, and the ln R over R0 is the factor alpha, and we know alpha varies not even 1 order of magnitude in practical cases. Let's say 1 order of magnitude, yeah, if they're very close together, dislocations, let's make this a little smaller, then they can vary maximum an order of magnitude. So we get a good feeling already what's happening there in dislocation energy. In more or less by 1 order of magnitude, half order of magnitude, depending. So this is the hand waving arguments we physicists have. We want to get the order of magnitude estimation, what is happening. And of course, if we design a metal or a device not to fail when the airplane flies, then we go for the more conservative numbers. Make it a little thicker or a little stronger. Right. And similar things turn out for the edge dislocations, as we only look to orders of magnitude, so we average over the sine and the cosine. And finally, we get this formula here, which is decorated by the 1 minus nu in the denominator again. Very important takeaway for you, and keep that in mind. This is important for qualitative reasoning later on. This W over R, so these strain energies of dislocations, they depend on the Burgers vector squared. So the magnitude of the Burgers vector squared depends on G, of course, but G is constant in the material. B depends. You can have any Burgers vector in the crystal lattice, but it depends, the energy it costs goes with the square. And also the edge dislocations, they have a slightly higher energy by 1 minus nu, because we know nu is something like 30%, 0.3, so this is 0.6, 0.7. So we divide by 0.7, we get something like 1.5 times the dislocation energy of a screw dislocation. Yeah, so here's the reason, the b squared, I mentioned it already. This is the reason why we always want to have short Burgers vectors and not the long Burgers vectors. You could do it, but it costs a lot of energy. Sometimes you have to do it. Right, so this brings us now to the force of a dislocation. What is the force on the dislocation? We have the external work. If we now look here to the edge dislocation, the external work is a shear force times the distance. So we have here the shear times distance, Burgers vectors. And the internal energy can be written as a force density times L. So this gives F. The big F is a small f times the length of a dislocation. So now the L is uppercase, before it was lowercase, times the distance. And then we put the two equal. So the external force equilibrates the internal force, and we get F equals tau times B. Very simple formula. F is the shear stress, the applied shear stress. Here we apply a shear here, tau, and tau there over that plane. And the force per unit length, so it's always the unit length here, equals tau times B, tau times the Burgers vector. Couldn't be easier. Once we have forces, we have energies, we have the stress fields around the dislocation, like the edge dislocation, with compression and tension, as mentioned. We can put another dislocation here and look what is the interaction between the two dislocations. For example, if I have a dislocation at this location, Then I have the compressive stress here. So this is, and I have the tensile stress there. I know this is tensile, the upper is compressive. So what happens? I have a compressive stress and I have a tensile stress. Of course, they attract each other, because if I put the tensile stress on the compressive stress on top of the tensile stress, then I have no stress if they're the same order, yeah? So I minimize the stresses if I put them, for example, on top of each other. Makes sense? This is shown here qualitatively. I have two dislocations on the same slip plane and the same sign, the same Borger's vector. So I introduce a plane here and I introduce another plane there at another distance x. And that gives me the compressive stress field for the first dislocation above the plane and tensile below. And here again, compressive above and tensile below. What happens? Compressive and compressive, if I would overlap these two compressive stress fields, then I need to compress more. If I need to compress more, it costs energy. So they repulse each other. They want to go away from each other. There are these forces, and these forces, they are repulsive. Opposite, on the same habit plane, if I have here the positive and the negative, so introduce a plane from the bottom, two dislocations, I have here the compressive field and I have there the tensile stress field, and the other way around below the plane, but tensile and compressive. If I move them together, then they just compensate. Strain energy goes down. So they are attractive. They attract each other. They have a net force attracting. Or let's look to those two situations where we have not the same habit plane. We have two habit planes. We have here and the other one is further down. In such a way that here we have the tensile and here the compressive forces. Then, of course, if I overlap this compressive stress field with this tensile stress field, then I minimize the stress field. So they move in this direction and in this direction. Let's say they only can move on the slip plane. They cannot climb up and down. And then I minimize. So this, they move together on the vertical line. Or else, here we have the situation where we have plane inserted to the bottom, plane inserted to the top, and see that then the compressive stress fields, they would overlap if I bring them together. So in that case, I want to separate these compressive stress fields to minimize the energy, and that pushes them away from each other. Again, I only can move on this habit plane. I cannot climb. I don't allow to go from here to there with the dislocation. At room temperature, I cannot climb. At high temperature, when I have diffusion, they can climb. They also can go up and down. Then it becomes important. But at room temperature, it's not important because I don't have diffusion to climb the dislocation. We remember, if we want to change the habit plane in the edge dislocation, we have to climb. And this is transport of mass. This is transport of vacancies. or interstitial atoms accumulating. So these are the interaction of dislocations. And again, you can, I explained it qualitatively here. You also can look it up with this diagram, which specifies the field here around the dislocation. I think intuitively it's quite straightforward, but this is the important thing you have to understand, the intuition. This is what you need to get used to. I have something compressive, I have something expansive, and I bring them together. What's happening to the energy? I have a compressed region, I have a tensile region. That gives me tensile energy, this gives compressive energy. I bring them together, while this compression and tensile expansion, they cancel more or less each other. Depends how much they overlap. So I have less energy. And a compressive and a tensile region, they annihilate each other, the stresses. They compensate each other. So that lowers the total energy. Right, let's look a little quantitatively to the interaction between the dislocations. So here in that sense of the repulsion, on one habit plane I introduce two dislocations, and when they're in far distance, so the one dislocation is far away from the other dislocations, so the overlap is negligible, then the total energy is just 2 times alpha GB squared over 4 pi. So this is now for screw, but the same you can write down for the edge dislocation. Now we put that all in the alpha, yeah? So you can put a 1 minus nu in the denominator, it doesn't change anything. So remember, 1 has a factor of 1 here, and 2 has a factor of 2 here. Because I have 1, which is independent far away from the other one. Now if I attach them, if I move that really to overlap with the other one, or just put 2 lattice planes into my crystal lattice from the top with respect to the bottom, then I double the Burgers vector if I put 2 lattice planes in. So this is when I put them as close together as I can. Means basically the Burgers vectors doubles. This is the close they can get together. And this b plus b squared gives a 2b squared, which gives a 4. So then I have 4 times the energy of one dislocation. So far away, they're just 2 times the energy. If I put them really next to each other, then it goes up to 4 times the energy of one dislocation. So we see they repulse each other because if I minimize the energy, they want to go apart from each other. And the other way around, here I introduce one from the top and one from the bottom on the same habit plane. And we can imagine already, if we put them really together in these inserted planes, they move together in the x direction, then I annihilate. I just have one continuous extra lattice plane through the whole crystal. So I have a perfect crystal. This is an annihilation of dislocation, we say. Gives a perfect crystal. So again, the distance, if they're far apart from each other, I just have the energy of 2 dislocations in the far field. So same as here, yeah? Doesn't matter, I insert them from the top and the bottom. They don't feel each other, so I get just the energy of 2 dislocations extra integrated over the whole crystal. But now I put them together, then I have to subtract the Burgers vector, because one Burgers vector is positive, the other Burgers vector is negative. Negative is when you insert from the bottom. So the energy becomes B minus B. The new Burgers vector becomes B minus B, which is 0. To the square is 0. So the energy due to those dislocations, when I put them together, becomes 0. That's why annihilation, dislocation disappears. When the dislocation disappears, I should have the energy of the perfect crystal. So now extra stored energy by dislocation. Extra stored energy becomes 0. Of course, there are all kind of energy landscapes in the crystal. Yeah, maybe surface energy increases because if you put, yeah. Okay, go into philosophy if you like. Here's the interaction between edge dislocation. Obviously, this is cool, right? This is wow. Little hand waving. But for edge dislocations, if we put it now into the formula, so first, the previous slide was more general. This is now edge dislocation, yeah. But for edge, you need the 1 minus nu here in the denominator. Doesn't matter for the arguments before. But now if we look quantitatively, we get the force. We said already the force is tau times B. Important formula. The force per unit length is tau times B. And the sigma Ri equals the sigma theta theta. Becomes this. Sine theta over R. And we have a Burgers vector there. And the tau theta R was with the cosine. Now if we look to the force as a function of theta, so the force as a function of theta, and of course R. So we have the polar coordinates, then it becomes sine 2 theta over R. For the theta component, and for the R component, we just get the 1 over R behavior. So GB squared over 2 pi 1 minus nu, same as before, this prefactor, times 1 over R. And let's put them in. So we say fx is, now we do the coordinate transformation from the theta and R to the x and y. So we result this formula fx, so those two formulas gives us fx and fy in the x and y direction, this constant prefactor all the time. And here we have x squared minus y squared divided by x squared plus y squared, which is the radius to the square times x. So it scales with x. And for the y component, we also get something scaling with y, but in the nominator we have here the 3x squared plus the y squared. So here we have a x squared minus y squared, and here we have 3x squared plus y squared. We said now, at room temperature, the dislocations, they can move along the habit plane. So they can move along x. So if I have a fx, they will move due to the drag by the force fx. But they also may have a force in the y direction. However, we said the dislocation cannot climb from one habit plane to the other. So we don't need to consider the fy. We know there's a fy, But it's not relevant at room temperature because the dislocation cannot climb. It will be important later on in the course when we talk about creep. But now we're not talking about creep, we're looking to this normal plastic deformation without diffusion. Here I plotted the forces between the dislocation in the glide direction. So this is just the Fx, it's the glide direction. The Fy is the climb direction, if we want to climb where we need diffusion. And they plot like this. So here I have positive forces. I think the one is a logarithmic or square root scale of the other figure because you don't see too much in this figure. So I put a emphasized figure there. I think square root or of the magnitude or so. Anyway, so qualitatively we see here the colors. We have positive here of two dislocations. So I have one edge dislocation, I have another edge dislocation here. If I put it here, then it's in the figure it would be here. And that gives me a force which depends on 1 over r squared. Yeah, we have here, this is something like squares of distances. Here we have the force power over distances times the distance, so 1 over r. Of course, yeah, 1 over r. Yeah, so here we have the positive. That means they are repulsive in this direction. The force goes in the positive x direction. If I put the dislocation here, the force goes into the negative x direction. In both ways, they repulse from the 0 position. The force goes away from the 0 position. So on the positive side, in the more positive, in the negative side, the force is pointing negative. But then we also have those locations here where we have a force dragging the dislocation into the negative direction. In the same here, we have a force dragging the dislocation into the negative direction. So what does that mean? That means this dislocation, if it has this drag force, will move until it comes here, or on the same plane, yeah, until it comes there. And you see here's no force, force is 0. And if I would go further, then the drag would go in the positive direction. That means here, in this direction, it is stable. So with respect to the first dislocation, the second dislocation becomes stable when it arrives just above x equals 0 of the first dislocation. So that's interesting. I can move, if I'm on the right side, it moves to the left if I'm in this quadrant. So if I'm in this quadrant or octant here, yeah, this one, this triangle, then it moves to the left. And if I'm on the negative side of this triangle, it moves to the right until I go to equilibrium position here just above x equals 0 and symmetric on the bottom, of course. So these are interesting locations. Note, there's also this 45-degree line, should be 45 degree, where the forces also become 0. But then, if I go a little to the right, if I deviate by some fluctuations to the right, then I go into this yellow field, where the forces become larger and larger, and I move away from this 45 degree. And the same, if I go to the left hand side of this 45 degree line, then the force goes further, drags further to the left. So this is an unstable equilibrium line at 45 degree, while here we have a stable, ST I put there, location, orientation. So okay, I may have dislocations here in the 45 degree, which are born somehow there, but eventually when they overcome the yield stresses, they move towards this stable line of arrangements. And that gives me dislocation arrangements. It's also shown here in those diagrams. So here we see again what I showed on the colorful figure just before. I put it can put it in MATLAB and plot it. Yeah, the formula. This is the formula, and here we can work it out. The force between the edge dislocation. This is when B1 equals B2, and this is when B1 equals minus B2. So this is when you put the edge dislocation upside down. The second one is inserted from the bottom. If you insert the second from the bottom, basically the figure turns around in having this attractive, repulsive behavior for B equals B2 as a function of x here at some distance y. So you plot this at some distance y. So this is 1 times y. You see this is 2 times y. This is 1 times y is a 45 degree orientation. In this figure, it's this line here. If you go 2 times y, so x is a function of times y. So basically, it's the orientation vector. Yeah, this x times 0 times y is here, 1 times y is there, 2 times y is there, 3 times y is there, and so on. So a half times y is this orientation. So these are the orientation vectors, or orientations, and depending on the orientation, I first have for B equals B1, if x is larger than y, then I'm in the yellow field here. If x is smaller than y, then I'm in the blue-violet field here in this upper triangle octant. So if I'm in the upper triangle octant, I get the attractive forces, the negative forces, which moves me towards x equals 0. If I go above the 45 degree line, which is here the 1 times y, then I get positive forces which drags the dislocation further away from the 0 position. So, means, yeah, sorry, if we now for B1 equals minus B2, so if the dislocations have opposite sign, then you can work it out and get the blue line, which is just inverted, yeah. And we see there's repulsion. There's repulsion if they are here in this quadrant, and there's attraction along that line. This line will be a local minimum. resulting if we have the same Burgers vector, then they tend to arrange in lines perpendicular to the habit plane, and if the two dislocations have opposite sign, then they tend to align along the other, this 45-degree minimum or zero energy becomes stable. Good. So here the stable positions for the two edge dislocation of A and the same sign and opposite sign B. So two edge dislocations with the same sign, you insert the plane here, insert the plane there, they align perpendicular to the habit plane, so in the 90-degree angle when you connect the dislocations. And if they have opposite signs, are either this up and that down, or the first down and the second up, then they align under 45 degree to the habit plane. That is interesting, because if you put many dislocations in and wait or anneal them a little bit, that they can move, and then the edge dislocations, they align like this. When we have the similar signs, and if we introduce a lattice plane every so and so often, the average lattice here to the average lattice orientation there gets a little inclined, because here we have always one lattice Burgers vector more. If we say now the distance, we can say the distance here and the angle, if this is theta half, the distance is approximately b over theta. That's for small angle approximation. Yeah, you can put the sine in, or expand the sine into Taylor. Then it's b over theta. Distance is c over beta, and so it's shown here. So we have a correlation between a low angle grain boundary, theta. Theta is the angle between this, we call a low angle grain boundary, and the distance between dislocations. This we call grain 1, which is a perfect grain. This we call grain 2, which is perfect grain, and they're inclined by each other by theta. That can be observed here. So with electron microscopy, you go around these loops, you find a dislocation, you see there's a Burgers vector here, there's another Burgers vector here, another Burgers vector here. Somewhere in here, it's difficult to locate it. That's why I said you better go around in a larger loop. You can make it even larger, and you find the Burgers vector. So we know there's a Burgers vector here, and we know there is now this regular arrangement of dislocations here and there and there and there. So you see nicely they put a wall, of course not 100%, yeah, on top of each other, because there's still this little energy to overcome, but more or less straight 90 degree above each other. And then if you look to the lines here, they will be inclined. So here we have lines like this, and here we have lines, I see them like that, and they have an inclination angle towards each other, which are described by this model. So if you look to the low angle grain boundaries, actually these are strengthening mechanisms, because the dislocations, they align along these grain boundaries, or they align like this here on top of each other. And if I move them away, if I want to move them away, it costs me energy. So if it costs energy, it makes the material stronger. And that's why we call this a strengthening mechanism. The low angle grain boundary is a strengthening mechanism. I'm in the potential minimum. If I want to go away, I need extra power. I need extra force, or I need extra shear stress, external applied shear stress to move these dislocations. So they are pinned, they are correlated to each other. Of course, if I make the shear stress big, they move away from each other. But it makes the material harder. So this is a strengthening mechanism. And one of the many strengthening mechanisms to inhibit, to hinder strain, dislocation movements, because dislocations make the material soft and ductile, but make it soft. If we can somehow fix the dislocation in place, in space, so that it cannot move, then we have a strengthening of the material. So the low angle grain boundary is a nice example of strengthening the material. And we can say the low angle grain boundaries, they are somehow defined by 15 degrees smaller or equal 15 degree. You know, in the crystal you have many 30 degree angles already, which are given by symmetry considerations. And so then you may go into another lattice plane or closer to small angles to other lattice planes. So if you go well smaller than 15 degree, then the low angle grain boundaries can be represented by an array of dislocations. So in particular, this low angle tilt boundary can be represented by an array of edge dislocations. So you have the edge dislocations, that's a particular example shown here. This is the grain boundary, which can be modeled like this. You put one edge here, next edge here, next edge there, and then in the far field you get the inclined crystal lattices. And again, so you can work it out. If theta is small, then the sine of theta half, you can put it by the argument, yeah. So becomes sine theta half is just theta half for small theta, and the distance becomes b half of dislocations, or this is the correlations between the distance and the theta. B over theta, sorry, not b half, b over theta. So that recalls dislocation walls. This is dislocation wall. These are randomly oriented dislocations, but if they are arranged vertical to each other, we call it a dislocation wall. Also, there may be an inclination between the grain boundary. So the grain boundary is shown here, this dotted line, and the orientation of dislocations and crystal lattice. So it can be asymmetric by this angle phi, because I can introduce dislocations which are sideways, yeah? So I introduce a lattice plane here from the left-hand side, from the right-hand side to the left. And then I have to superimpose the two and the stress fields of those. And that leads to the asymmetric tilt boundary. The second set of dislocation appears so that the boundary plane moves off the plane of reflectional symmetry. So this is a symmetry plane. And now this tilt boundary moves off this symmetry plane by this, well, this is the D for the one type of dislocation, this is the D for the second type of dislocation, and of course you have to swap the orientation, the coordinate system x and y, so the cosine becomes a sine here. And phi is the angle of inclination of the boundary plane with respect to the symmetry orientation. So this is a demonstration here in a simple cubic lattice. Now the energy of dislocation boundary is, for small theta, the distance between dislocation is large and the energy of the grain boundary is proportional to the dislocation density. So we have the distance is large and the energy proportional to the dislocation density, just the number of dislocation. But if we bring them close together, so when theta approaches 15 degrees, the core regions of the dislocation start to overlap. They come too close together and the cores, they overlap. And the description of the grain boundary in terms of dislocation wall is no longer useful. And that's where we get some saturation. So first we go linear up and then we get saturation. For random high angle grain boundaries, they are not described by these dislocation models anymore. High angle grain boundaries. We have to have other energy considerations. Also, what happens at the surface? So if you have a surface, let's say here's a surface, x equals 0, and we put dislocations in there, then we can handle that. There's a strain field. We can handle that by image dislocation on the other side with opposite sign for screw. And the image for the edge is just a negative dislocation there. And that gives us repulsion and attraction to the surface. So I can attract our dislocation to the surface or repulse our dislocation to the surface. And that's why dislocations can go to the surface and annihilate there. This is what I wanted to say today. Long story on the very short image dislocation here. I hope there's an explanation in the tutorial. We finished the lesson today because next time I want to go into other dislocations which are related to stacking faults in FCC crystals. With this in mind, I thank you for your attention and hope to see you again next time. Bye!